So today we are actually starting off with our first calculus topic. So yesterday we sort of reviewed some of the basics of calculus. If you weren't here, just the slideshow and the class recordings are available on Classroom. They should also be available on the Alphademic YouTube channel shortly. But this is our first calculus topic, and it's limits. So we will be going into that. So first, what even is a limit? Well, consider this function, right? I want to start out with an example. Consider this function right here. It's x squared minus 2x minus 3, all of that divided by x minus 3. And I hope this is a familiar, general type of function. It's called a rational function. That's when one polynomial is divided by the other polynomial. So in this case, the numerator polynomial is x squared minus 2x minus 3, and the denominator is x minus 3. Now, does anyone take a moment to factor the quadratic in the numerator, because the numerator of this fraction is a quadratic, and this can be factored. So just take a moment to factor it, and then type your answers in private to me in the chat. Mhm. All right. Okay, wonderful. So I have a lot of really good answers from pretty much everyone. Yeah, basically what you have to do is you have to factor the top, and the top is x plus 1 times x minus 3. And then when you divide it by x minus 3, we can cancel it, right? And we just get x plus 1. Now, the thing is that we can usually cancel it for x not equal to 3. When x is equal to 3, however, this results in 0 over 0. Right? Both the numerator and the denominator are equal to 0. And so we can't really cancel out the 0. So at x equals 3, this function is undefined, but it's just x plus 1 for all the other values. And we can visualize this graphically like this. So we have our function. It's pretty much the linear function x plus 1, right? Y equals x plus 1, except it's undefined at x equals 3. But we still would like to, quantify this function somehow at this point, right? And we noticed that if it hadn't been for this x minus 3 in the denominator, x minus 3 in the numerator thing, at x equals 3, x plus 1 is just equal to 4, right? And we can see here that this value, if anything, looks like it gets really close to 4, but doesn't quite reach there because at x equals 3, it's undefined. And so how do we quantify this function at x equals 3? Well, we can, instead of just thinking about how it's defined, right, at x equals 3, we can think about what it gets closer to. So here, the function gets closer and closer to 4. Like if we approach x equals 3, the value of the function will get closer to x equals 4. And so we can use this as an alternate way of quantifying the function at x equals 3 rather than just defining it there. So mathematically, this is written as the limit as x approaches 3 of f of x, in which case f of x is our red function right here, is 4. So lim just means the limit. This is pronounced x approaches 3. And then 4 is the value of the function had it been defined at 3. This is sort of the value that the function approaches as x gets closer and closer to 3. Is everyone good with this concept of functions approaching values as x approaches an input? Anyone have any questions so far? All right, since no one has questions, we'll move on to more examples. So the question here is, what is the limit as x approaches 1 of f of x, where f of x is this function right here? Again, notice that the function in the previous example wasn't defined at the input in question, which was equal to 3, right? It wasn't defined there. It doesn't have to be not defined there for the function to be able to approach something. Here, for example, at x equals 1, the function is perfectly defined. It's equal to -1. It also happens that the values of x approach, right, as x approaches 1, the values of f of x approach -1, which just happens to be the value of the function at that point, but it doesn't have to be. So in this case, the limit is -1. What about this function, though? Well, I want you to take a minute to think about this. What do you think the limit should be as x approaches 1 for this function? Notice again that it says undefined here. It's not really undefined because we defined it at -1. So basically, this is just a normal, smooth function until it gets to 1, where the value is actually -1. So there's this sort of jump over here. So what do you think the limit should be? All right. Yeah, take a moment to private message me. All right, so again, the question was, what should be the limit as x approaches 1? Do you want me to go over this, or do you still need a minute to think? All right. All right, at 5:42, I will go over the answer. So if you want to me to share the answer before then, just speak out now. Otherwise, I will wait until 5:42. All right, so I will go over the answer now. Even though the function is defined at -1, right, as -1 at x equals 1, the limit is actually 0. Why? Well, because the function clearly approaches 0 as x approaches 1, right? We can think about this way. At x equals 1.00001, the value of the function is much closer to 0 than it is to -1. Similarly, at x equals 0.9999, the function is very close to 0, more than any other value, right? And in general, we can think about what is the function equal to at values very close to the desired value, and then that should tell us what the limit is. So in this case, even though the function is defined at -1, the limit is actually 0 as x approaches 1. Is everyone good on this, or do you need like any clarification? Any questions so far? All right, wonderful. Again, if you have any questions, feel free to unmute yourself or type it in the chat. All right, this is a very tricky one, but I think that you guys can solve this. What's the limit as x approaches 2 of f of x? So here, I mean, on the graph software that I used to draw this graph, it's said that this is undefined. In reality, just think of this as two of the same function. This is all one function. You might recognize this as a step function, right? So this is equal to one constant, and then it abruptly switches to the other constant at x equals 2. However, it's defined at x equals 2 as 1. So the value at 2 is 1. But what's the limit? All right, take a couple minutes. I'll give you like a couple minutes to answer this question. At 5:45, I will go over the answer if you can't get it. So, and this is, by the way, a trick question. I'm going to say it right now. All right, so I will go over the answer now. This is actually a pretty tricky question, but there were people who got this right, so very good job. The answer is actually there is no limit. Let's see why this is, right? As x gets closer and closer to 2 from values that are less than 2, right? For instance, at x equals 1.99999, the function is equal to 1. In this case, it's equal because it's a constant, but it doesn't have to be. It could be very close to 1, right? At 2.0001, however, this function is very close to whatever this value is. I think it was a half, right? This is a half, by the way. I should have made that clear earlier, probably. That this is the constant value at all these points greater than 2 is a half. But basically, from the left, we say, right, this approaches 1. But from the right direction, this black arrow, it approaches a half. It doesn't approach one single value. So we just say that there is no limit. It simply does not exist at x equals 2. It exists at every other value of the function, just not at x equals 2. Now, we do have a special notation when these limits from the left and from the right diverge or don't have the same value. And in this case, we say we have this special notation for the right-hand limit. It's just the same as a normal limit, except we add this plus to the upper right corner of the value that x is approaching. So as x approaches 2 plus, meaning as it approaches 2 from numbers that are positively like greater than 2, we see that the limit approaches a half, and this is called the right-hand limit. From the negative side, right, as x approaches values that are 2 from values that are less than 2, we see that f of x, the limit of f of x is equal to 1. So the individual right-hand and left-hand limit exist, but the singular limit at 2 does not exist. Everyone good with this concept? Because it can get a bit tricky. All right, wonderful. So there are no questions, and I will move on to the next topic. So here we have this function, and this is the graph of 1 over x. And let's look at how this function behaves at this x equals 0 right here. At the value x equals 0, this function has an asymptote. Perhaps you recall this from algebra or pre-calculus, because if you plug in x equals 0 here, you just get 1 over 0, which is undefined. And so there's this 0 point right here where the function isn't actually equal to something. It approaches something, both from the right and from the left, but it isn't equal to that. What do you think here, I'm going to write this over here. What do you think? Clearly, there isn't one single limit at x equals 0. But what do you think the limits as x approaches 0 from the positive side of 1 over x should be equal to? What do you think? How do you think we should define this? All right. I'll give like 1 more minute until 5:50 for other people to answer. All right. So if you have some time to think about this, notice that this actually approaches positive infinity, right? Yeah, so correct, wonderful. So yeah, so the limit from the right-hand side of 1 over x should be positive infinity. This is because as x gets closer and closer to 0, this function gets bigger and bigger. And again, we will use the same like principle of considering values very, very close to our desired value. Like say x is equal to x is equal to 1 over 1,000, right? 1 over 1,000. Again, that's a value that's pretty close to 0. If we take its reciprocal, 1 over x is 1,000. However, if x is equal to 1/10,000th, then the reciprocal is 10,000. So we see that as x gets smaller and smaller in magnitude or closer and closer to 0 from the right, 1 over x becomes bigger and bigger, and so this limit approaches infinity. And that's actually a very important concept in calculus. Here we say that the right-hand limit as x approaches 0 of f of x is plus infinity. However, since there is no finite value of this limit, some people will just say that it's undefined there. But you could also say that it approaches positive infinity. Now we will introduce the concept of negative infinity. So positive infinity is infinity, but with increasingly large numbers, and infinity is greater than 0. And as x approaches 0 from the negative side or from the negative numbers, the same effect happens as from the positive side, just the reciprocal as a result is negative. And so the quantities of f of x in magnitude become infinite, but their sign is just negative. And so we have a term for this, it's negative infinity. And we can say that x, as x approaches 0, right, from the left-hand side, f of x approaches negative infinity. Then we have these other two concepts. What happens when x gets extremely big? When x gets extremely big, we can say that x approaches positive infinity. And notice that 1 over x gets very, very, very small and approaches 0. Similarly, the limit as x approaches negative infinity of f of x is also equal to 0. because 1 over a very large number in magnitude, regardless of its sign, is going to be very, very, very close to 0. All right, is everyone good with using limits, using infinities in limits and with the notion of negative infinity? Because we will use negative infinity later in our course as well.
Could you explain the bottom two? I understand the first like two, but bottom two, I was wondering if you could explain that.
All right, so basically as x approaches positive infinity, so as x gets larger and larger and larger in that direction, this function will eventually get closer and closer to the axis, and clearly its value will be 0, right?
Okay, so then like on the opposite side, when x is increasingly going towards negative infinity, it goes closer and closer and closer to 0.
Also, yeah, it gets closer and closer to 0.
All right, thanks.
Does that answer the question?
Yeah.
All right, wonderful. So I will move on to the next topic. Now here, we kind of go away from examples a bit and go into, a bit more theoretical stuff. Just hang in with me, and if you have any questions, make sure to ask them at any time. So there are a couple properties of these limits. Suppose that we have the limit of some function. We have the limit of some function as x approaches some value, and this function is scaled up by a constant. So for example, we can imagine if we had some sort of line right here, the line would get steeper, right? If like c is greater than 1 or something, or the line would just change its slope somehow. Maybe it would get shallower, we don't know, just from arbitrary c. Then this new limit is equal to whatever the previous limit was multiplied by c. All right. So pretty straightforward property. You might expect that, but it does require writing down. Everyone good on what this property tells us? Because this is probably like the simplest property of limits. So I just wanted to make sure that this is like firm and solid. Everyone good? All right. So the next property is that if you have two functions and you add them, say we have, I don't know, this function, which is f, this function, which is g, and when you add them, you get some sort of f plus g. Well, then, if this is the limit of just g as x approaches a, and again, here I'm using a equals 0, but it doesn't always have to be at a equals 0. This is just very convenient. And f, the limit of f as x approaches a, and we add those two limits together, then that should be the limit of whatever this new sum function is at x equals a. So everyone good with this property as well? All right. And we can visualize this on an example. Suppose we have these two parabolas, and we will call this red one h of x, and this blue one is g of x, which is 3 times h of x. And again, I'm using a equals 0 here, but it doesn't always have to be like this. We can use a equal to any value, and the same will still hold true. So notice how the limit as x approaches a, which is 0 in our case, of h of x is 1. And then if we multiply that by 3, we get 3. Similarly, the limit of 3 times h of x is 3. Right, so sort of like this. All right, everyone good on this slide? Because this is as basic as we will get in terms of limit properties. So I just want to make sure everyone's good on this. All right, because the next exercise will be a bit challenging. So, all right, using the previous two properties, show that the same thing works with the difference. The limit as x approaches a of f of x minus the limit as x approaches a of g of x is equal to the limit as x approaches a of the difference of the two functions. And so take like probably 5 minutes, or I'll give you until like 6 o'clock to just type this into the chat. Think this through using the last two properties, namely the constant multiple property and the sum of two functions property. I'll give you like 3 to 5 minutes to think about this. And of course, as always, type it in the chat. And if you need me to go back to the previous slides so you can see the properties I'm talking about, please just tell me to do so. I'm going to type the question in the chat, by the way, to everyone. Oops. Yeah, so I will now go over the answer. I hope you had a chance to think about this. All the answers that I received were correct, so that's wonderful. Again, don't be discouraged if you didn't get this. This is generally a pretty difficult problem for an introductory course, but I just want to throw this in there just to give you a sense of what the rest of the course will be like in terms of, letting you think about how we derive like certain mathematical problems. So we use the last two properties, right? And we start with this initial expression, limit as x approaches a of f of x minus the limit as x approaches a of g of x. And we can simplify this last part right here. All right, I'm gonna circle this last part right here by knowing that this is essentially -1 times whatever this is. And we can pull this -1 inside the limit by the constant multiple property. And so we get this limit right here. So right after that, we can now add the two limits, right, by the limit addition property. And then we just simplify the parentheses, and that simplifies to the limit of their difference. So again, the proof is pretty simple, but again, it's pretty challenging to think of this. So great job if you solved it, and it's okay if you didn't. All right, everyone good on these basic properties? All right, no questions, so I will move on to the next slide. All right, so here's just a review of the limited properties we have looked at so far. This one is the constant multiple property, the sum property, There's this other property that states that the limit of f of x times the limit of g of x as both f and g approach a certain value a is equal to the limit of their product as x approaches a. Again, fairly intuitive. We won't go over the proof here, but again, this makes sense, I hope. If it doesn't, make sure to tell me. I will try to explain a bit better. We have the same quotient property. By the way, this follows from if we have this, then we can just say that this is multiplied by 1 over the limit of g of x, and then we can basically just substitute the inverse of g of x, right? And use this property right here. So this follows from the product property. And then one more property that's maybe a bit less intuitive, but still I hope it generally makes sense. If you have some sort of constant c, and you raise that constant c to the power of the limit, again, doesn't have to be an integer, just some sort of power, then this is equal to the limit as x approaches a of the constant raised to the power of the function. All right. So these are the 5 basic limit properties that we will derive everything else in the course regarding limits from. Does everyone understand these? Because if you don't, then it will be a bit hard to follow along later on. All right, no questions. I will move on to how we actually evaluate these limits without a graph. So consider this limit of a linear function x plus 1, right, as x approaches 1. Note that x plus 1 is just a linear function. It doesn't have any weird asymptotes, no like jumps, none of those holes that you saw on the graph. It's a very simple, quote unquote, smooth function, right? It's just linear. In this case, what we can do is we can just plug in x equals 1 into the function, right? Because it's defined at x equals 1, and it's like a smooth curve. There are no irregularities in it anywhere. Not just at x equals 1, but anywhere. Again, by the way, this only has to be true at x equals 1, that there are no irregularities for this direct substitution method to work. In our case, it just happens that this function also has no irregularities anywhere else on its domain. So the answer is 2. So this is direct substitution generally. Now try this example. What should the limit be of sine of x minus 2 squared, right? The inside, the x minus 2 is squared, and the sine is taken of that as x approaches 2. All right. Just take a minute to think about this. Okay, so again, we can just use direct substitution here because sine of x minus 2, sine of x in general is defined everywhere in its domain. Squaring the inside and subtracting 2 from the x doesn't change that fact. So sine of x is defined everywhere. It has no irregularities because just sine is just like a sinusoidal wave. It looks like, it just looks like this. So of course, sine of x squared is a bit different, but it's the same general principle. So we can just substitute x equals 2 into this expression, and sine of 0 is just 0. So that is the limit. This is the most simple way to evaluate a limit. Of course, it doesn't always work because the function could have an irregularity at that point. And we can think about this by visualizing the next function. So this is the limit as x approaches 2 of 1 over x minus 2. Try to evaluate this limit using direct substitution and see what happens. So just like plug in x equals 2, and what happens? Can you evaluate this limit? All right, so I will go over the answer. Plugging in x equals 2 yields 1 over 2 minus 2, which is 1 over 0. Now, dividing by 0 in generally means this is undefined. But let's look at what happens on the graph. So notice that this is, by the way, the graph of this function, right, of x minus 2, of 1 over x minus 2. And you'll see that it actually has very similar behavior to 1 over x. And it's because this is exactly the same function, just shifted over to the right by 2. And at x equals 2, this actually does not have a limit because from the positive side, this is infinity. And from the negative side, it's negative infinity. And even if they were both to approach in some sort of infinity that had the same sign, that limit would still be undefined because it was infinite. Here it's just undefined. You can't refer to it as plus or minus infinity in terms of the general limit. What you can do is you can say, oh, the limit as x approaches 2 from the right-hand side is positive infinity. From the left-hand side, it's negative infinity. In general, without the graph, this is how you can tell that there is an asymptote. When the limit is of the form c over 0, where c is a non-zero constant, for example, 1 is a non-zero constant, it's not equal to 0, then there is an asymptote. So for instance, if like we have 2 over x minus 2, and we want to find the limit as x approaches 2, right? Then that would yield 2 over 0, and 2 is a non-zero constant. So that means that there is an asymptote at that point. Everyone good on how to identify asymptotes without using a graph? All right. So now this is a bit more tricky. So this is the limit as x approaches 0 of 1 minus cosine of x over 2 times sine of x squared. So let's go through this together. We'll try direct substitution. Direct substitution is always the first thing that you should try when evaluating a limit. Always. Even if you have a hunch that it might not be defined, always try that first. It might just work out. So if we do direct substitution, we get 1 minus cosine of 0 over 2 times the sine of 0 squared, which is 1 minus 1 over 2 times 0. And this is 0 over 0. Notice how we can't tell that there is an asymptote, because an asymptote is when c is non-zero. But what happens when it's 0? Well, this is called, so a limit of the form 0 over 0 is called an indeterminate form limit. This means that the function is not defined at that point, of course. The function is not defined at x equals 0, but the limit might still exist, right? So there might be a hole, like, for example, the graph could look something like this, where it's just not defined at a certain point, but the limit certainly does exist. It could not exist. We don't know until we simplify the function a bit more to find out. And typically, how we determine which indeterminate form limits are do actually exist is we simplify the function. So we simplify algebraically, right? Sine of x squared, this is again a pretty basic trigonometric identity, is just 1 minus cosine of x squared. And again, this is just the most basic trigonometric identity. If you're unfamiliar with this, I did post a brief Khan Academy course on this on the Google Classroom if you need a refresher. And now we can use difference of squares. 1 is of course 1 squared, and then we subtract cosine of x squared. We get cosine of x times 1 minus cosine of x. So now within the limit, we can actually cancel. Even though 1 minus cosine of x is equal to 0, right? We don't care what happens at x equals 0. We care about what happens as x approaches 0. And at any non-zero value, even if it's really close to 0, 1 minus cosine of x is not 0. So we can cancel it. And we cancel the 1 minus cosine of x, and we get 1 over 2 times 1 plus cosine of x. This can no longer be indeterminate because there's a 1 on top. And now we can try direct substitution again. So let's try again. Substituting x equals 0 into cosine of x yields 1, which is really nice because 1 over 2 times 1 plus 1 is 1 over 4. And this is the value of this limit. Is everyone good on how I routed this, or do you need a bit of an explanation? If you do, that's totally fine. Like this is a pretty difficult limit, but it is necessary for what we'll do later in the course. So if you have any questions, please speak out now.
I have a question.
Yeah.
Can you go to the last slide?
Last slide.
Yeah, the other slide. Yeah. So basically, you find an asymptote by c over 0, and if c is non-zero, then that means we have an asymptote. And this is for limit functions, right?
Yeah. So when c is not 0, then you have an asymptote. Like
Yeah. Okay. Yeah.
Yeah.
So
Here,
we're evaluating a limit function, and whatever we get is non-zero, like what we just got, like 1/4. That will be our asymptote, correct?
it won't be an asymptote though in that case. That's just whatever the limit is equal to, right? That's just the value.
Okay, I see.
An asymptote is just like a vertical line. So
Yeah. All right.
So yeah, but yeah, in that case, we actually do have to do some work.
All right.
Does that answer the question?
Yep.
All right, wonderful. Any more questions? All right, so I will move on to the next limit, and this one we will also do together. Find the limit as x approaches -3 of this function right here. A lot of students, when they see limits as x approaches 3 from the negative side, they often confuse it with the limit as x approaches -3. Don't do that. So this is -3 because the negative is to the left of the 3, and not 3 from the negative side because the negative is not to the right of the 3. So just in case you were, because sometimes when I was first learning calculus, I did get those two mixed up. I made silly mistakes, so don't do that. Anyway, so let's try direct substitution. Is the first thing we try. When we plug in -3, we get 0/0, right? -3 plus 7 inside the square root is square root of 4, which is 2 minus 2 is 0. This is an indeterminate form. The function is not defined there at x equals -3, but the limit might be defined. We just have to do some work to find what it will be. So typically when we see a square root in the denominator, one of the first things we do is multiply by the conjugate to get the square root out of the denominator. In this case, this is also a necessary tool to find what the limit is. If we multiply by the square root of x plus 7, all of that plus 2, right, on both sides, we just get a difference of squares here. The square root of x plus 7 is squared. We get x plus 7 minus 2 times 2, which is 4. So this is just x plus 3. Then we have x plus 3 times square root of x plus 7 plus 2. The x plus 3's can cancel. Again, at x equals -3, they don't. But for any value x, even if it's really close to -3, but that's not equal to -3, they can cancel. And so here we just get this value, and here we use direct substitution to get a limit of 4. By the way, multiplying out the conjugate is not just useful for getting radicals out of the denominator. Sometimes when you have this indeterminate form, but the radical is in the numerator, you might actually need to get the radical into the denominator, which is not something you might be used to, but you might have to get the radical into the denominator to actually be able to evaluate the limit. All right, is everyone good with this example? All right, let's see how much time I have left. Oh, yes, okay, wonderful. What time is it, by the way? For some reason, my clock on the computer doesn't show up.
5:16.
5:16. Okay, so we will go past this example, and we will go on to our last topic for today. This is the squeeze theorem. So yeah, 6:16. Oh yeah, I understood. Don't worry. So if we have a function f of x that's bounded from below and from above by two functions g of x and h of x, and both of their limits at a certain value a are equal to L, where L is a constant, right, a defined constant, then the limit of the function in the middle is also equal to L. Here's what this looks like graphically. We have a function f of x that's less than h of x, or less than or equal to h of x, but greater than or equal to g of x, right? The green one is f of x, h of x, g of x. H of x and g of x are the same, have the same limit at this value right here. in order to, I like to visualize this as passing through the two functions. F must pass through whatever this limit has to be. So the limit of f of x will also be L. This is also called the sandwich theorem. This is also called the sandwich theorem because you can think of f being the, filling in the sandwich, like the meat, and h of x and g of x, the bread, right? The meat has to go through the bread. So this is a very useful theorem, squeeze/sandwich theorem. Everyone good on this? All right. So I will go on to our very last example. This is an important limit that we will cover, but I promise this is the last example because I know it went a bit over time. Yeah. Yeah, so the limit of f of x will be equal to whatever the limit of g of x and h of x are. Generally, they would also be equal, but for instance, f of x might not be defined at that point, or h of x or g of x, they might not be defined. As long as they have a limit here, right, they might not be defined, but as long as there is a finite limit that's not plus or minus infinity, this theorem applies. That answer the question? All right. Good. So this is the last example. So the limit here that we want to evaluate is the limit. It's an indeterminate form limit. The limit as x approaches 0 of sine of x over x, right? When we plug in x equals 0, this is an indeterminate form. So, and actually algebraically manipulating this is kind of hard. Here's a way that we can do this using the squeeze theorem, right? So first we draw the unit circle, right? By the way, this diagram is from Khan Academy. Khan Academy is a wonderful resource to learn about all of this. That's how I self-study calculus. But yeah, anyway, back to our main point. So this is the unit circle. Its radius is 1, and it's centered, sort of in the coordinate axes. And let's just call this variable right here x. I know it's called theta here, but let's just call this x right here. So this angle is x, that's the angle. The radius of the circle is 1. And so this length right here, this red length, has to be sine of x. Notice that opposite over hypotenuse, right, is sine of x, and it has to be the sine of this angle. So this red length is sine of x. Now, this white arc right here, can everyone see my mouse? Yeah. Okay, so no, so I assume that's a yes. This white arc right here is x, right? This is just the angle measured. So this white arc right here is x. And notice that x will always be greater than sine of x, right? This is longer than sine of x for, x's that are pretty close to 0, right? Again, we want x close to 0. Like again, for x in the third or in the second or third quadrants, this may not apply, but we want x that are close to 0, so this actually does. And so since I'm going to change the format back to black, since sine of x is less than or equal to x, again, it's only equal to when x equals 0. We get that sine of x over x is less than or equal to 1, right? Just dividing the x out on both sides. Now, notice that this white length right here, this one right here, this is 1 also. That's another radius. And so this blue length has to be tangent of x, because this blue length over 1 has to be equal to, opposite over adjacent is tangent of whatever angle this is. And so this blue length is tangent of x. Now note that tangent of x is bigger than x. So tangent of x is bigger than or equal to x, again, for x close to 0. But tangent is just sine over cosine. Sine x over cosine of x is greater than or equal to x. And then multiplying out the cosine on both sides and dividing both sides by x yields sine of x over x is less than or equal to cosine of x. Right? Like this. And so sine of x over x for x close to 0 is both less than 1 and greater than or equal to cosine of x. right? So we have this inequality right here. Now we can think about this as this function is h, this function is g, and the middle one is f. Note that as x approaches 0, cosine of x will approach 1. Cosine of x will approach 1, right? So, of course, the limit of 1 is 1 at any value. The limit of cosine of x as x approaches 0 is 1. So the limit of sine of x over x as x approaches 0 must also be equal to 1. All right. So this is a very, very important limit. I mean, it's one of the sort of most basic examples of this squeeze/sandwich theorem, and we will use it later in this course as well. Does everyone understand how I got here to limit as x approaches 0 of sine of x over x equals 1? Again, it's a complicated proof, but if you ever need more clarification, both the slideshow and the recording will be posted on Classroom at the end of the class. All right, wonderful. So in that case, we will move on to the our recap. So in order to evaluate limits, we always try direct substitution first, right? That's always the first thing we go to. If you get a limit that yields an asymptote, right, c over 0 for non-zero z, try values that are close to the number that x approaches to see if the limit approaches positive or negative infinity. If you get an indeterminate form, you have to simplify, right? You might get into some messy computations, but that's the only way you can really evaluate this limit for now. By the way, later on in the course, we will have a very, very powerful technique to evaluate these indeterminate form limits without all that messy simplification. But that will require our next topic, which is derivatives. So again, keep an eye for that, something to look forward to. Finally, if you can find two functions that bound the function whose limit you are evaluating, you can use the sandwich theorem. So anyway, I hope everyone found this helpful. This is our class on limits. And yeah, any questions at all? All right, again, I know I went a bit over time, but I just really like that last example, so I had to share it with you. Anyway, so have a good rest of your day, and the next class is tomorrow. The topic will be continuity. Anyway, so have a good day. Thank you for coming.